Okay, welcome back. Here's another type of torque problem that we can solve, but this kind of uses the idea of moment of inertia to help us solve things with torque. So just a recap of torque. We can write torque as force times distance times sine of the angle. That's one way we could look at torque. The other definition of torque looks like F equals ma, where we use basically, F as tau, m is the moment of inertia, and a is alpha. So actually I'm going to use both the definitions in this problem to solve a little bit about the person throwing a ball. So let's start with part one. Part one here says that we need to find the torque. It says that the mass of the ball is 3.6 kilograms. We have a linear acceleration of that. And if you could see from here, here's the axis of rotation. So from here to here where that ball is located, I'm going to write r as 0.31 meters. So we do actually have this. So the question is, what is the torque needed? So in this application, I actually want to use this form of our torque. So torque is equal to moment of inertia times alpha. And you can see why, because alpha right here can be related. Now if you remember, alpha is equal to r, let's do that. Well, it doesn't matter. I can write it like that. But I'll write it the way I have it on my slides. A is equal to r alpha, like that. So alpha, A over R will give me my alpha, which is what it's needed to, solve this problem right here. Oops, there you go, put the equal sign like that. So let's go ahead and do that. Now the other thing we need to do is figure out I. Now it says ignore the mass of the arm. So if we do, then the only thing we have here is a ball, which actually acts as a particle away from our level arm, r, like that. So if I for a particle is going to be mr squared, like that. So what we have is tau, the torque needed, is going to be mr squared times alpha, which is going to be our A over R, like that. And then what you can see is one of the R's cancel. So MRA is going to be our torque, which is all the information we have. 3.6 kilograms times R times A. And when we solve this out, 3.6 times 0.31 times 7, we get a torque of 7.81 Newton meters, like that. And that's our net torque, like that. So that's the torque needed. But now the question is, part B is the force that the muscle must exert by the tricep. So here it is. This is a difference. Is the tricep muscle right here has a, the distance from here to the tricep right there. You see that right there? That's 0.25. So this is going to be, the torque here is going to be the same torque here. So we're actually going to still use this 0.81 Newton meters. However, our new level arm is 0.25 meters. Notice I immediately converted it from centimeters. So I'm actually going to use this form. Now you can see that in this case we have our level arm like that, and our force from the tricep is at a right angle like that. So with that said, our sine of the angle is 90. So we're just looking for that. So tau is equal to force times r This is 7.81 Newton meters like that equals F times 0.025 meters. And then if I do that, our force that's needed is going to be 312.5 newtons in order to create that same torque. Basically, the force needed to be exerted. So the force has to match that torque, and that's the force right there. So that is problem number 38. Let me grab problem number 39. Okay, I'm back. I grabbed the other problem, not problem 39. This is a statics problem. Again, we're going to use torque. Another way to use torque. So in this problem, what we have is we have this person at the end of the diving board, and we're looking for force of A and B. First, we'll not include the mass of the, ignore the mass of the board, and then we will. So let's start with part A. So looking at this person, although she's over here, I guess I'll just, yeah, we'll just assume she's at the end of the board, right here. It's going to apply a force downward with her weight like that. Now this is perpendicular, so we don't have to do any signs. This will also supply a force, so this will, I'm assuming this is going to apply a force upward. If this is going down, this is going to be up. And then I'm going to guess at the direction of A. I don't know the direction officially. And if any of these are ever wrong, I'll get a negative sign, which means I made it backwards. So let's assume this is the case, because it looks like if I did it like this, the system would be at equilibrium. Okay, so we're looking for FA and FB. So just a note, if we use Newton's laws, just the sum of the forces in the y, we can set it equal to 0 because the system is in equilibrium. But as you can see, if I were to do it like that, I have FB is positive minus FG of the person minus FA equals 0. You can see that I have FA and B as unknowns, so two unknowns. But what we could do is actually use torque to eliminate one of these unknowns to solve for one. So I can eliminate an unknown by choosing a pivot at one of the forces. So I'm going to actually choose my pivot here. So my pivot like that. And if I do that, we know that if I apply a force to that location, there would be no rotation. So there's the benefit of that. So then it comes down to saying basically, just like I have over here, the sum of your torques have to equal to 0. So another way I could write this is, again, counterclockwise is positive minus the clockwise, they have to equal to 0. So let's analyze our system. So if you look at this, this is going to make a clockwise torque. This one would make a counter. So that would make a positive and that would make a negative. And notice again, we don't have to include A because it's not part of our problem. So torque counterclockwise would be the following. It would be, and these are both perpendicular, which is really nice. So I don't need to do any signs. So my first torque is this one. So it's going to be the mass of the person, or mg, times this radius. So for the 3 plus the 1, so this is going to be 4 meters. Just a reminder, torque is force times the radius. And if these things are perpendicular, you can leave it like that. Minus the torque by this one, which is the FB, and that is 1 meter away. Let me say that's equal to 0. So FG is going to be equal to mg of this person right here, which we actually have. The person is 58. Okay, so mg, I'll just rewrite this times 4. and then minus FB basically equals 0. Obviously times 1 will make that just FB. So what we have is M is 58 kilograms times 9.81 times 4 minus FB equals 0. 58 times 4 times 9.81, 2275.92 newtons minus FB equals 0. And then obviously you could have done this shortcut earlier, but if you move that over, we find that this is in fact the force from B. And it turns out I chose the upward direction, so this is positive, so good. Now let's, so now that we found this, we can use the equation that I have over here to find A, because now we have FB. So, I guess I'll do this in a different color. So this was basically step 1. Step 2 is to use this relationship to solve for A. And I'll do that by just moving this over, so you can see that FB minus the weight of the person is going to equal to that. So here we go. FB, which is going to be 2275.92 newtons, minus the mg is equal to FA. So this minus mg. So the force in the A is 1706.94 newtons. So that is the magnitude of the force. And since this number came out positive, that means I chose the right direction. In other words, this is going the way I defined it, which is down like this. Sometimes I don't know, and it doesn't matter as long as in the end you can kind of figure it out. So the fact that it's positive means I chose this direction as negative, because I implied this as negative before. So moral of the story, that is the official final answer for the force of A, like that. So let's find out what happens when we do include the mass of it. So let's erase this and start over. So this is a board right here. Now we're going to include the mass. Now this is a uniform board, so I assume around 2 right here is our center of mass, where this thing is going to be pulling down with its weight. Call it mg1. And this is going to be pulling down with its own weight. Same case, oops. We'll assume that B is up, and we'll assume A is down. Essentially, we just have another term. I'm actually going to solve this the same way, but now I'm going to take into account the masses, the board's mass, like this. So, the sum of the forces in the Y should equal to 0, or according to my diagram, force B minus force A, because that's down, minus mg1, because that's down, and then minus mg2. So I said mg, but remember fg is mg. And there we go. So we're left again with the 2 unknowns. So that's my first, well, this is going to be my second step. But my first step is to, once again, do my torques by choosing this as my pivot to eliminate A. So pivot. And then look at all these radiuses. This is 1, from here to here is 2, and from there to there is 4. These are all my radii. And we'll do the torques again. So we're going to take the clockwise torques and subtract them from the, the counterclockwise, subtract from the clockwise to give 0 Newton meters. This one is going to be